Now let us consider here the reflection of a traveling electromagnetic wave along the x-axis from the interface, which is the yz plane, and here we consider the electromagnetic wave incident normally on the interface, no oblique incidence, normal incidence. And here we consider the reflection and transmission coefficients. That means how much part of the incident wave is reflected back and how much part is transmitted through the second medium. Because if this is considered the incident part is 1 unity, then a fraction of it will be reflected back and a fraction of it will be transmitted. Now here we first calculate the amplitude, reflection and transmission coefficients, how much part of the total amplitude is reflected back and how much part is transmitted. And then we calculate the average power, that means intensity. We know that the intensity is proportional to the square of the amplitude. So then how much intensity of the incident wave is transmitted and how much part is reflected back. Now let the interface is separated by the yz plane. Here it is the medium of refractive index N1, this medium has the refractive index N2. Now here we consider that the incident wave is traveling along the x-axis, so its electric field is vibrating along the y-axis and magnetic field along the z-axis. It is a polarized wave. Actually in the electromagnetic wave, the electric and magnetic fields are vibrating. Suppose this is the x direction, it is traveling along the x-axis. Then in this plane, in the yz plane, the electric and magnetic fields will vibrate randomly in all the directions. But here we consider a polarized wave to show that the vibration of the electric field is confined in a particular direction along the y-axis, and the vibration of the magnetic field is confined in the z-axis. Now, the frequency of the waves are same, as we know it is a fundamental property omega, and propagation constant in medium number 1 is k1 and in medium number 2 is k2. Now, when the reflected wave, in the reflected wave the electric field is represented in the negative y-axis, but the magnetic field is in the positive z-axis, same direction. And in the reflected, transmitted wave, the electric field is in the same positive y-axis and it is in the positive z-axis. Why it is flipped over? Because to make it consistent with the propagation of the energy, because the energy of the electromagnetic wave will travel along the x-axis. Wave is traveling along the x-axis, energy will be propagated along the x-axis. For the transmitted wave also it is propagating along the positive x-axis, but the reflected wave is propagating along the negative x-axis. So what is Poynting vector? That is S is equal to 1 by mu 0, say E cross B or E cross H. Now the energy is propagated in the direction perpendicular to both E and B or E and H. Now here its energy of the reflected wave, which is traveling along the minus x-axis, it will travel along the minus x-axis. Then if we flip both, that is E is going to minus here EY, it is in the negative y direction. If we make it minus y, then it will change its direction. But if we change both, E is going to minus E, B is going to minus B, then it will not change its direction. Then either you have to flip the electric field, you have to draw either electric field is in the negative y-axis or the magnetic field in the negative z-axis. If we draw EY in this direction, EY prime, then Z will be in the negative z-axis. So either E is minus E or B is minus B to make it consistent with the direction of the propagation of the energy. That's why the electric field here we consider vibrates along the negative y-axis. Now similarly, the transmitted wave electric field of the transmitted wave is along positive y-axis and magnetic field along the positive z-axis with propagation constant K2. It is in the another medium. Now let us represent the E1y, H1z, E1y prime, H1z, everything in terms of time varying field. Because the electric and magnetic field will vary with time and space. So how they are represented, as we have written earlier. So E1y let the electric field is represented by E1. It is vibrating along the y-axis. So we write AY. It is the unit vector along the y-axis. E1 y e to the power I. Propagation constant is K1. K1 dot R minus omega. So H1 is vibrating along the z axis. So AZ H1z e to the power I K1 dot R minus omega t. So E1 and Z1. This is the incident wave and reflected wave or reflected wave E1 prime. It is vibrating along the negative y-axis, that is minus AY. It represents the negative y-axis. Amplitude is E1 y prime e to the power minus I K1. Actually K1 dot R, here it is traveling along the x-axis, so K1 dot R, actually only the x component will be there, so K1, you write it is K1x, so here also it is K1x, it is traveling along the x-axis only, normal which we have considered, so here it is K1x plus omega t. Now because this wave is traveling along the minus x-axis, so you put here x is minus x, so you get minus ik1x plus omega t. So it is here because it is traveling along the negative x-axis. Similarly, h1 prime, this one, it is also traveling along the minus x-axis. You get az, it is traveling, it is vibrating along the positive z-axis. No minus is here. h1 z prime into e to the power is like this minus I k1x plus omega t is the reflected wave. Similarly, for the transmitted wave, or transmitted wave, what we get E2 is equal to AY E2y e to the power I k2x, because the wave number is different, minus omega t, and here you get H2 is equal to AZ H2z e to the power I k2x minus omega t. So these are the representation of the electric and magnetic fields of the incident and the reflected and the transmitted waves. Now, we know that the ratio of the amplitude of the electric and the magnetic field is the speed of the light in that medium, that is E by B is the speed of the light in that medium, or we can write E by H, B equal to mu 0 H, to get it is mu 0 into V. What is V? In terms of the speed of the light in vacuum, you can write C by N. V is equal to C by N, B equal to, we write mu 0 H, and V is equal to C by N. C is the velocity or speed of light in vacuum. Therefore, from this we can write H is equal to, magnetic field is equal to N by mu 0 C into the electric field. Therefore, here H1Z H is this, H and E is relation this, then H1Z. H1Z is related to, say, E1Y, that is N by N1 by mu 0 C E1Y, because in the first medium N is N1, so you get H1Z is equal to N1 by mu 0 C E1Y. Similarly, you can write, say, H2Z and H2 prime. So H1 Z prime for the reflected wave, that is N1 by mu 0 C E1 Y prime, and H2 Z is equal to N2 by mu 0 C E2 Y. Now, if we apply the boundary condition, this is the boundary interface. Here we apply the boundary condition, that is the tangential components of both the E and H are continuous here. As the tangential component of electric displacement and magnetic induction B, normal components are continuous at the boundary. Similarly, tangential component of the electric field and the tangential component of the magnetizing field H are continuous at the boundary. So the tangential component, applying the boundary conditions, applying the boundary conditions on E and H at the interface, that is at the YZ plane, we get it is the tangential component of E1y plus E1y prime will be equal to E2y. Okay, but normally in sequence they are the tangential to the surface. Now, therefore, if we apply this boundary condition, then what we get? That E1y minus E1y prime, minus because it is in the negative y axis, that is equal to E2y. Suppose this is the equation number 1. And for magnetic field, that is tangential component of H1 Z plus H2 H1 Z prime, because both are plus, both are in the positive x axis, Z axis, is equal to H2 Z. Now, if we substitute the value of H1 Z, H1 Z prime, H2 Z prime in terms of this electric field, and if we substitute here, then what we get? Here N1 by, you get mu 0 C into E1 Y plus E1 Y prime is equal to N2 by mu 0 C into Y. So you get N1 into E1Y plus E1Y prime is equal to N2 into E2Y. So this is another equation, equation number 2. So you get two equations. Now from these two equations, this is one equation and this is another. Now if we multiply this equation by N2, multiply equation 1 by N2 and subtract it from equation number 2. So multiplying equation 1 by N2 and subtracting from 2, what we get? Here we get N2 E1 Y minus E2 E1 Y prime is equal to N2 E2 Y. So this will cancel, minus plus minus. So this term will cancel. So here you get relation between E1 Y and E1 Y prime. That is E1 Y prime you get N2 minus N1 by N1 plus equation number 3. Now we get U1y prime. If you substitute this value into equation number 1, substitute this value of E1 prime in equation number 1, that is here in this equation. Then E1 prime will be eliminated and you get a relation between E1y and E2y. Substituting, three in 1, what we get? We get a relation between E2y and E1y. E2y in that case you get twice n1 by n1 plus n2 E1 y. Now therefore, this is the amplitude of the reflected wave electric field, amplitude of the incident electric field. So this is the ratio amplitude reflection coefficient. Therefore, the amplitude reflection and transmission coefficients are, there is reflection coefficient R12, that is ratio of E1y prime by E1y, that is E1y prime by E1y. How much portion is reflected? So that will be equal to E1, that is N2 minus N1 by N1 plus N. This is the amplitude reflection coefficient. Similarly, amplitude transmission coefficient T12, that is ratio of this by this, that is 2n1 E2y by E1y, that is 2n1 by n1 plus n. So these are the amplitude, how much part of the total amplitude is reflected back and how much part is transmitted in the second medium. So this is in terms of amplitude, and we know that the square of the amplitude is proportional to the intensity. Now we calculate the power, transmitted power and reflected power. Now, so we have to calculate it in terms of the energy flux, that is in terms of the Poynting vector. So the reflecting and transmitting flux or power that is Rn, reflecting power, that is the ratio of the reflected flux or power by the incident flux. That is into in terms of the pointing vector, the S prime reflected power by S, the average value of the pointing vectors. Similarly, the transmitted flux Tn transmitted flux by incident flux there is S2 by S1. Now this side stands for the average value. Actually the value of the pointing vector S, both electric and magnetic fields are perpendicular to each other, that is 1 by mu 0, we write E cross B or E cross only H, then we get 1 by mu 0. If E and B are perpendicular, we get EB. But electric and magnetic fields are vibrating, is a time varying field. So when we take the average value over a complete cycle, then a half factor will come. So you get the average value of the pointing vector, that will be equal to half 1 by twice mu 0 EB. Now if we calculate the average flux from this, then you get 1 by twice mu 0 E. What is B? E by B equal to V. E by B equal to the speed, that is C by N. So E is equal to, or B is equal to, you can write N by C into E, or H is equal to, B equal to mu 0 H, you get N by mu 0 C into E. Now if we substitute this value here, then what we get? B N by mu 0 C into E. So we get N by twice mu 0 square C into E square. So transmitting flux Rn, the reflecting flux. So here you get S prime, E will be replaced by say E1 prime here, E1 y prime. That's what you get. Here the total number is E1 y prime square. So the square is there, and here you get N divided by twice mu 0 square C. Similarly for S, S is similarly E1, you get E1 y square. Here you get is N1, here you get N1, and this quantity will get here twice mu 0 square C. So here you get E1 y prime by E1 y whole square. So Rn that is equal to R12 square, because E1 y prime by E1 y is equal to R12. So R12 square, that is its value is N2 minus N1 by N1 plus N2 whole square. This is the power, reflecting power. This much power is reflected in terms of the refractive indices. Similarly, transmitting power Tn is S2 by S1. So here you get it is N2 by N1 T12 square. If we calculate these in terms of that, then it will come N2 by N1 T12 square. So you get 4 N1 N2 by N1 plus N2 whole square. Now we revert back if there is no absorption in the interface, in the second medium, then if we revert back the reflected and the transmitted rays, then it will again produce the incident ray. So that means in that case, in case of no absorption, you get say Rn plus Tn, that must be equal to 1. You see, Rn plus Tn will be equal to 1. It is in the case possible, in the case when there is no absorption, because the light is falling on this medium must absorb something. And we consider here that the medium is absorptionless, there is no absorption. That's why we take the refractive indices as real quantity, but refractive indices are not actually real quantity. Whatever may be the medium, when the light will fall on it, some part will be absorbed. Whenever you revert back this reflected ray and the transmitted ray, it will not again produce the incident ray. Some part will be absorbed. But for the time being, we consider that the refractive indices, when we consider they are real, there is no absorption. But actually, there is absorption, and refractive indices are not real quantities, in general a complex quantity. Okay.